Hello, everyone, and welcome to my channel. This is Sohini from South Bay, California, and welcome to my channel today. Deep apologies for being away for the past couple of months. Between settling into a new job, a new role at work, and publishing 3 single-authored papers while being a mom, time just got away. So sincere apologies. However, things are getting more into a routine now, so I should be able to release 1 to 2 videos a month for sure going forward. So thank you all for your continued, tuning in into our channel and for the continued support. I've been overwhelmed the past couple of months with the amount of, messages that I've received in LinkedIn and over, YouTube and in my emails about how this channel has literally helped you towards your thesis, towards starting a new project, and how you find this whole community useful. So thanks a lot. I highly appreciate your comments. I go through every one of them. So please, please, please do leave me a comment or send me an email or feedback, and I'm more than happy to get that into maybe a next video idea or even start a new playlist corresponding to it. One observation from my past couple of months has been that we have 2 very separate categories of audiences on this channel. Now, one audience is they are very well versed with this idea of AI machine learning. They really want to know what is new, upcoming, what are the cutting edge technologies that is happening. And they want to be able to, for me to review and cover all those topics. And then we have a second category of listeners and audiences who are just beginners into AI and machine learning and who really want me to help them, break down the very nitty-gritty ideas into small bite-sized lessons. So going forward, what I'm going to be doing is I'm going to start 2 separate playlists. One is going to be advanced AI and machine learning for, machine learning enthusiasts, where upcoming blogs, models, I'm going to be going over papers. I'm going to go over new GitHubs and code bases and reviewing what is already up and coming. And the second playlist is going to be the bite-sized introduction videos, where you get into the key concepts and ideas or even jargon that you need to know in order to have even conversations with people who know machine learning and AI. So please do look out for those 2 new playlists. Additionally, I have been seeing that some of you have been reaching out with some of the wonderful work that some of my audience is working on. So I am going to also start another playlist which is called Workshop with Sohini, where you get to share your ideas on this platform to all our audiences. So please do check out or stay tuned for that as well. So if you are new to machine learning, where you would like to have a framework where you can import any new data set and always follow a set of rules or guidelines to make sure you have the optimal feature space, and also you are taking into account the data imbalance problem that occurs so very commonly whenever you are trying to model machine learning into the real life data sets that typically have data imbalance. So if you have interest in understanding or getting this new code base that I'm going to be releasing with this video, please do stay tuned, subscribe to this channel, and hit the like button. So let's get straight to it. Let's start this session by understanding what the data imbalance problem in machine learning truly is. Now, machine learning gives you tools in order to make better decisions by understanding the analytics and insights that are at hand. So based off of some observations that we call data or samples of data, you can then make a judgment call if you should progress or do something or not. For instance, if you're looking at stock market, based off of the stock market prices over the last month, how the economy is doing, you can start making assessments. Is the price going to increase for the next day or for the next week or not? Now, these are very simplistic examples of what machine learning tools can do. Now, there are 2 key important aspects that needs to be considered. First off, a machine learning algorithm or a model will be only as good as the training data that is used to train itself. And second, it is extremely necessary to ensure your training and test data sets have the similar distributions of the underlying samples as much as possible. Otherwise, if you train it on a very different distribution and you're testing on a completely new distribution, your results are going to be off. So going back to the stock price example, if you are estimating the stock prices in, let's say, India, based off of the economic, data that you have in India, and then you're trying to, predict the values in US, your results are probably not going to align just because of the fact that your training and test data sets did not have the same underlying data distributions, right? Now, let's try to understand what imbalance in data distribution actually looks like. So this is an example of a well-balanced data set that typically you learn in schools, or typically you will see in typical experiments and examples whenever you are learning a particular machine learning algorithm. This, you see, these are handwritten digits, all from 0 through 9, and this is how the representations look like in the feature space. As you can see, the idea birds of the same feather flock together holds, and you will see all the zeros forming their own clusters, sixes forming their own clusters, twos, ones, they all form their own clusters. But as I'm telling you in this example, it's a well-balanced data set. That means the number of samples corresponding to each handwritten digit is actually very similar, in which cases the models and their performance are going to be very different from the realistic case where all of the samples typically do not have the same number of samples. So let's take a look at what that would look like. So if I am to isolate, let's say, only the 0 samples, and to look at only these 915 samples. And here, if I now further color these by their color coding, you will now see that there is way more of 0. There are fewer samples of 6, some of 4, some of 9, and in which case the same classifier or the same decision-making tool that you had that was working for a well-balanced data set may not work if you had such a limited data set. So try to understand here, whenever we are trying to train a machine learning algorithm, it is impossible to have all data, right? So there is an inherent amount of bias that creeps in because of the number of samples that you have. However, if we are not cautious about the sampling distribution, what will happen is the performances could actually be biased, and we would not even figure out if it was biased or not if we did not know what these underlying data distributions were. So in today's example, we are going to take a look at what happens when you have a biased data set, wherein you have too many samples of one kind and too few samples of another kind. So for today's task, what we are going to be doing is, going forward, I am going to be releasing all of any of the new code that I'm going to be showing in this particular GitHub, which is called AI with Sohini Notebooks. And today we are going to be looking at the sample imbalance or the data imbalance problem altogether. So you see, this is the whole notebook, and in order for you to run the notebook, just right click on open in Colab, and this is going to open your own Colab session. The first task you should always do is go to File and say save a copy in Drive. So you should try to not run this algorithm from the place where it is already at. So let's try to understand what the data set is first, and then I'm going to show you steps so that you can ensure that the final outcome that you have is free, or as free as possible, from the data imbalance problem altogether. Now, this work actually comes from a latest publication from me and a few colleagues, and that's the publication that is marked on top. So think about it, this data set actually is an e-commerce data set. So there is this data set corresponding to a portal where multiple people have actually been going and purchasing products. And the information is tagged in the following way. So there is a product ID, and there is a user ID. You have no information about the user. So no name, gender, zip code, no nothing. It's just a random user ID code, created corresponding to every single person sign up. And also, and then if you are looking at products, what is the, range of the values of the products that you've been looking at, and again, then there are some temporal features as well corresponding to what time of day, month, and so on and so forth. So the first task that we do in this case is to look at the user journeys. Now the user journey, how we create this user journey is we combine all of the sessions for every single user product combination. So let's simplify this problem. Let's say that you want to purchase a car, and you go to the car's website or you go to a dealership website and you are looking for a particular car of interest, and maybe you keep browsing for a few weeks or even a few months before you come up to your final judgment call that yes, I am going to be purchasing this car. So this whole process where you logged in onto the portal and you browsed all of the different options that you have in order to finally make that purchasing decision, that is what we call as the user journey. Now, let's get back to the code base that we have at hand. So the first step, as I said, is in order to combine everything, and then we also do one hot encoding. So these are processes to do some data pre-processing. Now, let's start with the data set. And this is where you can modify this whole process to suit your data set. So here we are actually looking at, this Walmart data set. So this was, based off of a Walmart sort of a online portal where people are going in and purchasing cosmetics per se. So you have a user ID, you have a product ID. And as I mentioned, this is a journey. So you literally have the number of events, the number of times the person has logged in, and in order to create this journey, the number of sessions, the total interaction time, and for the things that you put in your cart, what is the maximum price, the minimum price, and the number of times you have taken a cart, the number of times you viewed, the number of times you've removed, and also some of the temporal features such as what time of day. And finally, the most important aspect that you are trying to predict here is, did this person make a purchase or not? So for instance, if it is things like cosmetics, the chances that the person is not going to purchase, unless the prices are all in the same range, is pretty low, right? So they're coming onto the portal, they are spending a lot of time, mostly they are going to purchase. However, if we go to expensive products such as an iPhone, or if we are looking at cars per se, then the chances of making a purchase is actually way lesser, right? So that's the reason why your purchase percentage, so the number of zeros, which says that there was no purchase made, versus the number of ones, which tells you that the number of purchase was made, is going to be imbalanced. So the number of zeros is not going to be equal to the number of ones. Ideally, the number of ones is going to be much smaller than the number of zeros, and this is the data imbalance that we are talking about. So this is where we are looking at every single numerical feature by the data frame.describe feature aspect. Now let's start to look at why there is data imbalance. So as I mentioned, if I just take all of the purchase values, so if a purchase was made, then the label is 1. If a purchase was not made, the label was 0. So now you see the percentages of purchase in the whole data is 12%. That means only 12% of all of the events resulted in a purchase. So there are 88% which did not end up in a purchase. So you see there is a huge amount of data imbalance. It is not 50-50, not 50% 0 and 50% ones, but actually 88 and 12%. So that's the reason why in this case, even if you use the right tools or the right machine learning algorithms, you have to sit down and think back if your model is doing what it's supposed to or not. Now, the first step, and this is the reason why I'm releasing this, this code base, so that if you have your own data set, feel free to reuse this code, because this gives you the whole structure as to the steps that you should follow whenever you are applying a machine learning algorithm. The first step is always trying to figure out, is there intercorrelations between the features? So are the features too highly correlated between each other itself? And the reason for this is, if you have features that are intercorrelated, then their individual contributions towards the label is actually much lower. So that means you should only consider uncorrelated features whenever you are trying to find their contribution towards predicting if a purchase was made or not. So step number 1, eliminate correlations. Now, in order to do this, we come up with this 2x2 correlation matrix. And in this case, you see all of the features that are intercorrelated have a lighter color, and we are supposed to eliminate them in this case. So that's what we do. That's what we go about, and we eliminate features that are highly correlated. And this process shows us that now from 35 features, now we get down to 33 features. So 2 features were found to be highly correlated and they were removed. So that's the first process that we go about doing here. The second process after that is to visualize this feature. So Are these top features that you are saying that are not correlated, are they really helping you to figure out was there a purchase or not? So this is using the Seaborn library, and what you can see here is it's showing you how every single feature is helping you make this distinction, was a purchase made or not. So you see in certain features like the feature number 1, you can definitely see the distribution for a yes or a purchase yes versus a purchase no are distinctly different. Like in some cases, it's not that distinctive, right? But in there are certain features that are definitely showing that they can tell you was a purchase made or not. So that's just a way of visually figuring that out. Now that we have taken all of the data set, now this is what you should do as a machine learning engineer. You should always split the data so that you have a separate training data and a separate testing data. 175,000 samples for training and 75,000 samples for testing. That is what we are going to be using. And then on top of this, what we are doing is, in order to further assess what is the importance of every feature, we are applying the random forest. And here, this actually gives you a beautiful result. This shows you that this is the order in which the importance of every single feature is reducing. So the most important feature is here, the second important feature is here, and the third, and so on and so forth. So one key finding from this is, if you see all the temporal features like that are related to time of day, day of week, all of them, they become not important. And so the other features, like how many times has this client removed products, or how many times have they added have they added stuff to their cart, or how many times have they viewed it, interaction, all of this becomes important features, but all of these temporal features become very less important. And in this case, what you can very well do is eliminate the temporal features altogether, because they are not that important anyways. And then I create this function in which I'm going to be visualizing the scatter plot in terms of the true positive, true negatives, false positive, false negative. So whenever you are trying to make a prediction, is this in this test sample, is this sample going to end up in a purchase or not? Either it will be correct or it's going to be false. But even the correct or false, it could either be a false positive, that means you're over predicting. It was actually supposed to not be a purchase, but you're over predicting. And in the other case, it could be a false negative. That means you predicted that there's going to be no purchase, but ideally there is going to be a purchase. So you missed something. So finally, in your final outcomes, you should have as minimum of the false predictions as possible. So that is what we are trying to be doing in this case. So the first step, because this is a classification problem, we start with the logistic regression. That's a very simplistic tool that you have at hand. So if we start with the logistic regression model and we are printing the confusion matrix, the confusion matrix, again, always remember the way you read it is, this is the true positive, this is the true negative, this is the false positive, and this is the false negative, right? So you want to reduce the false diagonal, which is these two entries, and you want to maximize the true diagonal, which is these two entries, right? And this is showing you the figure as well. So ideally, you want as much of red and blue in your final distribution, and less of green and less of cyan in your final distribution. So in this case, you see the accuracy is 74%, and precision is 31, and the recall is 46. So recall and the F1 score is 46. So F1 score is actually showing you highly important purchases. So it is biased towards the purchases rather than the non-purchases, right? And in this case, accuracy is actually a not good metric. So this is the first learning from data imbalance problems, that accuracy should not be used as a reporting metric, because an accuracy gives the same importance to zeros and ones, but in your data set, there is a data imbalance. So you cannot put the same amount of importance to zeros and the ones. So as you see in this case, although the accuracy is 74%, the F1 score is 0.46. So in these cases, F1 score or even recall and F1 score should be the metrics of importance. Now let's try another model, which is support vector machines. And in this case, I'm applying a support vector machine with the tolerance of 10 to the minus 3. Now, if you had used accuracy as your metric, you would have said, hey, support vector machine is doing way better. It's 88% accurate. However, if you look at the F1 score, it is way lower. It is just 17%, corresponding to the logistic regression where you had 46% as your F1 score. Now let's try to understand why that is. So this is a typical way in which support vector machine, which has not been tuned, behaves. What it tries to do is it has a propensity for the majority class. So in this case, the majority class is 0. So what this classifier is trying to say is, in order to make sure that you are highly accurate, I'm just going to predict all my samples are going to end up in no purchase. And if I do that, I still get 88% accuracy, because remember, the data imbalance had shown that the number of the percentage of samples in the data is 88%, belonging to 1. So if you just closed your eyes and blindly said that all my transactions are not going to end up in a purchase, you would still be 88% accurate. So that's why in these cases, accuracy should not be used as a measure. Rather than the right measure to use here is recall, which you can see is very low, and also F1 score, which is very low. So that's the reason why in this case, support vector machine should not be used as a tool, even though accuracy shows that it's a high value. Now that's all to do with the linear classifiers. Let's start with some non-linear classifiers. So we start with the gradient boosted trees. Again, gradient boosted trees, they are supposed to be extremely favorable for data imbalance classes, especially because of the fact that they consider very short decision trees, right? So they are very favorable for the bias variance problems. So in this case, as you see again, accuracy is actually much higher. It's greater than 88%. It's about 91%. And you see that the number of false detections is way lesser than what you had for your support vector machine. And even your F1 score, now you have a 48%, which is much higher than what you've seen so far. Now that we have looked at some standard classifiers, let's look at 3 different strategies that you can use or implement whenever you have data imbalance underlying in your data set itself. The first strategy is called class weight. So for a simple random forest classifier, if you just mention what the maximum depth is, and again what a random state of the classifier is, you will get a certain amount or a decent performance. You have about 91% accuracy and 28% recall and 44% F1 score. So again, there is some decision being made around the zeros to be zeros and the ones to be ones, but it's not very super highly accurate. However, in this case, what we can do is apply the class weight based penalty. For instance, here, understand there is 88% samples corresponding to class 0 and 12% corresponding to class 1. So for every of the test samples, if we increase the weight or the voice of the sample once and we decrease the weight or the voice of the sample of class 0, then we should ideally be getting better solution. And that is exactly what class weight does, is it weighs every single sample in the inverse proportion to the number of samples for that particular class that you have. So you see in this case, by using this class weight as a separate parameter to the function call, now you can get 92.5% accuracy and a very high F1 score of about 58.7%. So you see the false detections are pretty low in this case. Now, however, always remember, this is going to work when your test and your training data sets have very similar distributions. However, if this does not match, then your class weight imbalance is actually not going to be very helpful. So that's why there are 2 other methods. The first one belongs to this library called IMB-Learn. So IMB-Learn is designed to take care of class imbalance data sets. And in IMB-Learn, there is this classifier called the balanced random forest classifier. What it does is, rather than just calling a normal random forest classifier, if you call a balanced random forest classifier, it is going to subsample the major class. So 88% corresponding to sample 0 and 12% corresponding to sample 1. What this algorithm is going to do, it is going to subsample all the samples from purchase type 0, so that you have 12% of each. So you get equal number of samples corresponding to zeros and ones. So it undersamples, and using only the undersample data, it then fits your models, and here you get about 51% accuracy. Similarly, there is another process of oversampling. So it is called SMOT, or synthetically oversampling your minority class. So in order to apply SMOTE, again, it belongs to this class IMB learn, and it is called a random oversampler. Just as you saw in the previous case, we undersampled the class 0. In the same way, you can now oversample the class 1. So in this case, all the purchases that were made, you can generate, it's like synthetically generating more samples, so that again, at the end of the day, you have equal number of samples corresponding to zeros and ones. So the three methods: first is class weights, second is undersampling the major class, and the third one is oversampling the minor class. Now these are the three methods. If you apply them, in which case you will be able to figure out which is the best one. So for this data set, we saw that the class weights was actually the best case, and that is what we use for reporting. I hope you found that useful, and please do leave me a comment if you found this code useful as well, and look forward to catching you again in the next session.